Hello and welcome back. So in the last video, I mentioned that I was talking to my students and showed them about residuals and that sort of thing. And likewise, here I am in my office again. And this time, I wanted to review a data analysis activity that we had in class because it was particularly illustrative in lots and lots of different ways. So I'm gonna go ahead and go through that real quick and kind of reproduce what happened in class, and you can kind of see the thought process of a statistician and how that works out, and also see some of the things I think about as I'm doing data analysis and that sort of thing. So without further ado, we're gonna go ahead and go to R. So this data set comes from an actual article, and I have left a link in the description to the original article. And yeah, so let's go ahead and get started. And so the research question that we're going to investigate is the effect of internet addiction, which is labeled as IAT total score on depression, CESD, after controlling for health. So this is what you would typically consider a multiple regression, a conditional analysis and that sort of thing. Again, if you want to learn about what conditional analysis is, see the video linked in the description. So I'm going to go ahead and start by saying head D, just because I like to see what my data set looks like. Another way you could do it is STRD, but I'm going to go with that. And so the first thing that I do before I begin any analysis is I just look at the univariate plots. And I'll even write a comment to myself, univariate plots. So I'm gonna go, let's see, flex plot, IAT total scores, tilde1 data equals D. That right there, that tilde1 is basically telling FlexPlot you just want to look at the univariate distribution of that. So in this case, it would be a histogram. And by the way, I named my data set D earlier because I'm lazy instead of like health, depression, or something like that. And so if we plot that, I'm gonna make that screen bigger. What we see is we've got a positive skewness. So most people report, so IAT is internet addiction something or other. So most people report very low levels of internet addiction, and it's very rare for somebody to report extreme internet addiction. So that's kind of interesting. That could be a problem. Usually, well, this is a predictor variable, so usually we don't care about the distribution of the predictor variables, but it's something to look out for. We might see some skewness. So that's that. I'm going to go ahead and hit copy and then paste down below. And so instead of IAT total scores, now let's go ahead and look at CESD. So I'm just getting a univariate visual for each of the variables that I'm going to be looking at. And just like IAT, we got CESD, or depression. It is also positively skewed. Most people are not very depressed, which is great. And the higher the score, the less likely it is somebody's going to be that depressed. And then flex plot, we're going to do HPLP tilde1 data equals D. And I just thought of something. If you are following along at home, make sure that you got this part right here. FlexPlot is the package I developed, and these aren't going to work unless you require FlexPlot. So HPLP, that's just kind of a total score of their health behaviors. Oh, and it looks like, so actually FlexPlot gives you an error. It says, ruh-oh, somebody done made a mistake. Looks like you either spelled something wrong or included a variable not in your data set. And sure enough, I use HPLP when the actual variable is, there it is, HPLP total scores. So that's not gonna work out. But if I do it this way, we've got a fairly symmetric distribution. There's some deviations from perfect normality, but you would expect this in a data set with a sample size like this, which is row D 503. So that's a pretty big data set, but not so big that you would expect this gorgeously beautiful normal distribution. So anyway, I'm not worried about that. That looks pretty okay to me. So now that we've done the univariate visuals, I'm actually going to make a note to myself that says, hey dude, there's some skewness in IAT and CESD. Could be a problem when modeling. And so that's just a note to myself that, hey, this might fix things up. We actually Don't care what the univariates look like that much, as long as the diagnostics check out, which I'll show you that in a minute. And so now we can do a model plot, I like to call it, which is all the models at the same time, or all the variables at the same time. So I'm going to go CESD tilde IAT total scores, and then that pipe I say given, and basically what that does is it tells FlexPlot that the variables that come after this, I want you to panel those, and you'll see what I mean in a minute. So then we can put HPLP total scores data equals D. And then if I plot that, that's going to show all my variables at the same time. And what it's done is, in the background, automatically it has dissected HPLP total scores into kind of a low, middle, and high. And then it gives us these lowest lines. And so far, this looks pretty good. And well, you're probably asking, okay, what are you looking for? Actually, let's go ahead and add another option. We will go ghost.line equals ray. And so this is going to paint a ghost line. If you don't know what a ghost line is, I'll leave a link in the description. But basically what it does is it repeats this line, or you could actually have it reference this panel, doesn't matter. But it repeats that line across the other panels, so it's easier to compare visually what's going on. And so what am I looking for at this point? I'm looking for straight lines, because if there's straight lines, which they do look pretty straight, then what I can do, I'm going to put this on a new line, so comma, I'm going to go method equals LM. So these lowest lines are going to turn into regression lines, and now they are straight, and it makes it easier to do the second thing that I'm looking for. So again, the first thing I'm looking for is kind of bendiness, and second thing I'm looking for is the degree to which the lines are parallel. Because what I want to do, it is in my best interest for the sake of my brain to see if we can fit just a main effects model with no interactions. Because once you put interactions in the model, it gets a little complicated. And so what I'm looking for is I'm looking for fairly parallel lines. And to me, these lines look pretty parallel. Now, I had one of my students say, well, but don't you have this line crossing in these two panels? And that's actually a very common misconception. People think that if lines cross, that means there's an interaction. That's not true. Lines can cross without there really being an interaction. This could just be the only reason that they're crossing is because of sampling variability. So it could be that in the population, or the quote-unquote true line, that those lines are actually parallel, but just because you're collecting a sample of only 500 people, they happen to intersect. So you're not looking for whether they cross. What you're looking for is whether they deviate from being parallel. So if I had a line that went like this, that would certainly indicate that there's an interaction. Likewise, if I had one that never even crossed, but still was, super steep relative to that, then that would say there's an interaction going on here. And so at this point, when I did it the first time, I said, this is a simple model. Awesome, we can just do a main effects model. But then I thought, well, you know what? We should probably look at this from a different angle. Because right now we have IAT total scores on the x-axis. And what we've done to HPLP is we've compressed it. So it used to be a variable that ranged from 8 to 120 with lots and lots of unique values. And now we're putting everybody from 8 to 49 into one group, and from 49 to 65 into a second group. And so we are artificially compressing the visual, because we have to, because our brains can't really conceptualize three-dimensional plots very well. And so anytime you are doing multivariate visualizations, it is extremely important to plot it from different angles. And so rather than putting IAT total scores on the x-axis, I'm going to put HPLP scores. And I'm going to, follow the same pattern, put IAT total in a panel. And then now what happens, actually one thing that I should do is, instead of going method equals LM, because remember here when I did method equals LM, I only did that because the lowest lines looked basically straight. But if I do put the lowest lines back in, holy moly! Look at that. We've got, not only do we have non-parallel lines, we've also got this bendiness going here. We've got a nonlinear term, a potentially nonlinear term. And so this is a perfect illustration of exactly what I mean. When you plot just one multivariate graphic, it is very easy to be deceived. And so that's why it's extremely important to make sure that you look at it from lots and lots of different angles. And so to me, this says that there's potential that we might want to model a quadratic term. And so to do that, we go method equals quadratic. And when we fit the quadratic model, look what happens. We've got these pretty severe bends in the data. And notice also that in middle and high internet addiction scores, the relationship is convex upward. I think that's the term, convex upward, whereas in low IAT scores, it's convex downward, or concave maybe, I don't know. Anyway, but basically the nature of the interaction, or the nature of the bend is completely opposite for the low people, or for the people who have low IAT scores. So this presents some unique challenges, and this is exactly why we need to visualize the data first, because maybe the model, or maybe the visuals say, well, the model that you originally wanted to do, yeah, it's not a good model. And so at this point, I'm inclined to try to fit a linear model. Well, I'll just make notes to myself. So, well, maybe I'll make it up here, just to keep things consistent. So there is clearly, or I shouldn't say clearly, evidence of a nonlinear effect of HPLP on CESD, and possibly an interaction too. And that's because, again, we go from concave upward to concave downward. And so now what I'm gonna do, and by the way, I am not in confirmatory mode right now, so doing a p-value doesn't make sense, and I recognize I'm not p-hacking because I'm being completely open and transparent, but I am doing what I call rough, or what Tukey called rough CDA, or rough confirmatory data analysis. And see the paper linked in the description for a paper that I wrote explaining what this is. But basically, we're in a situation where we have a vague hypothesis, but we don't exactly know all the details or all the decisions we need to make. So right now, I'm just trying to find a model that seems to fit the data quite well. And so to do that, I'm going to create a model called full_model. And I'm doing a full model because I'm going to actually do a model comparison. And so I'm going to call one the full, one the reduced. So to do that, I'm going to go LM, and then I will just copy some of this. So CESD tilde IAT total scores plus, and then we're just going to copy and paste that. Copy HPLP total scores. And by the way, if we were just to ignore the visuals, that right there is the model that we hypothesized at the beginning. So it says we have two linear effects, two main effects, and we want to know the effect of, what was it? Internet addiction, IAT total scores after controlling for HPLP. And it's customary to put the variable that you are interested after the variable you don't care about, but it actually doesn't matter. Mathematically, it's identical. And so now yeah, that's right. That's what I would do if my visuals weren't suggesting something else, but instead I've got to add some information. So remember, we have this nonlinear relationship, so we need to tell R that we want to see a model of that. And to do that, it's actually a little bit awkward, and there's a reason for it. I'm not going to go into it, but we're going to go HPLP total scores squared. It would be nice if you could just type that without the I, but R requires you to put an I, and that's just R telling you in advance, by the way, this thing right here, the squaring that I'm doing, I need you to actually square the variable. Create a new variable that is HPLP scores, that is just the square of the original variable. And so that right there will take care of the bendiness, but look what's happening. We've got a bend going up here and here, but a bend going down here. So that tells you that there's an interaction effect, And it's not as simple as just adding the interaction between these two. Because if we were to go IAT total scores colon HPLP total scores, what that would tell R, or tell the computer, is we want to model a situation where the slopes are different. Okay, so if we wanted to model that where you're just looking at the interaction without the polynomial, what you're basically saying is the nonlinear term here, it might be here in one situation and here in another situation, or here, but the actual concavity of it, it won't go like this or like this or like this. You're just saying that the slope of it will change. And that's clearly not what we're seeing in the flex plot. So what we want to tell the computer is that sometimes it's going to go like this, sometimes it might go like this, sometimes it might go like this. Or, I'm having a hard time. It's all backwards. So we need to tell R that the shape of the polynomial itself is going to change. And to do that, shrink this again, put it over here, and hide myself anyway, whatever. So to do that, we actually want to model the interaction for the polynomial, which is like that. So this is telling R that the shape of the polynomial or the bendiness of that polynomial changes depending on people's IAT total scores. And so we could also, by the way, tell R, I'm gonna make that full screen. We can also tell R that its slope differs, but I don't see evidence of a strong slope effect, so I'm just gonna leave that there. And then we'll go data equals D. And so that is going to fit the model. Now, most people, they would start, not even with this because they don't have the visuals to inform them, but they would start with the full model and then immediately compute the estimates. But I don't even know if these estimates make sense. And so first what I want to do is, all right, I visualized it here. Now I fit a model and I want to see the visual representation of that model. So to do that, I go visualize full_model. And this is what we get. And by the way, the first time I saw this is actually a little embarrassing, maybe, in front of my students. The first time I saw that, I said, what happened to my curviness? Because this model right here, let's look at that again. This model said there's a lot of bendiness we need to model. But then once we model the bendiness, and then we look at it, we say, what? Where'd that bendiness go? And I puzzled over that, and I thought, this doesn't make any sense. And so I told my students it didn't make sense, and I said, I don't know why FlexPlot isn't behaving as it should, because the model produced by FlexPlot should be essentially identical to that. Not exactly identical, because FlexPlot in the background will model the interaction with the linear part. And I was seeing this and I thought, what is going wrong with FlexPlot? And one of my students was super brilliant and super wise and realized that, hey, you remember when I plotted this? And I put IAT total scores on the x-axis? Yeah, guess what? When I do visualize, you're basically telling the computer, I don't know what the formula looks like, just visualize it for me. And that's great, except in this situation, where it is visualizing something you don't want it to do. You want to put HPLP on the x-axis. And fortunately, we can actually tell R to do that. So we're going to go formula is equal to, and then we're just going to copy and paste this formula. So you can supply it a FlexPlot formula. So rather than letting it choose for you, you are telling it exactly how you want the formula to go and exactly what variables on the x-axis. And not surprisingly, we get a plot that looks almost identical to this one. Now, one problem with what FlexPlot is doing, and I didn't notice that until today, and I'm going to fix it as soon as I'm done producing this video. What Visualize really should do is it should show the exact fit of this model, but instead it's showing lowest lines. And so I just need to fix that. But if I were to do that, it would look nearly identical to this. So again, excellent illustration of the fact that if you look at it from different angles, different insights will emerge, and any one angle is necessarily going to be shortchanging your interpretation. Well, I shouldn't say necessarily, because sometimes the interpretations you make from one condensed view is going to be the same as another view, but in this case, it is very, very different. So, we've got a full model that has those terms, and to me, I look at this and I say that is a pretty strong bend. So if I were to make a judgment call based on this visual, and again, not having analyzed these data before, I would say that's a pretty strong polynomial there. That's a pretty strong quadratic term there. But it is very easy to be fooled by visuals, so it is always, always, always a good idea to pair the visuals with some numbers. So we're going to create a model called the reduced underscore model, and that is equal to LM, and then this time, well, I'm just going to copy and paste that just to save myself the effort, but now I'm going to remove all the polynomial terms, and instead I'm just going to add a simple interaction, IAT total scores colon HPLP total scores. And so now we're saying, yeah, forget those polynomial terms. We just want to compare the full model that has the polynomial to one that doesn't. And now we can use another flexplot function called compare.fits. And what we're going to do is we're going to provide our flexplot formula, which, oh wait, that's right. Formula equals that. So I'm just copying and pasting that. So I'm telling flexplot how I want the visuals to look. And I'm going to go data equals D. And then now it can accept a model, so we can go full underscore model. But you can also, again, it's called compare fits, so you can ask it to visualize two different models. So we're going to go reduced underscore model. And so now what we're going to get, so I got an error here. It says reduced model not found. Well, duh, you got to run the model, dude. And then you can do the compare fits. And now it's giving me another error. By the way, I try to make flexplot as informative as possible. It says, sorry, but some variables in formula don't match what's in the model, specifically a couple of things. So, where did I go wrong here? Okay, so that's one problem, is I put IAT total score, but I need total scores. Okay, and let's see if that will run now. Okay, yeah, that run. So, dumb mistake, I just spelled it wrong. I should probably come up with a more informative error message, but at least that got me in the right direction. All right, so now what do we got? So now we've got our visuals, and so we've got two lines. So the blue line represents the fit of the reduced model, which just says that that there are no polynomial terms, and then the red line says that there are polynomial terms. And so what I'm looking for is I want to see how similar the predictions are for these two models. And so what I'm noticing is that in the middle, and for the majority of the data, they actually generate very, very similar predictions. The only time they generate different predictions is at the tails. So that could mean that our polynomial model was actually trying to fit some outliers, and the only reason that bends upward is because of that outlier. Or it could not be, and this is a little bit ambiguous, and again, this is where statistics come in. So we got a visual that compares them directly, which is nice and helpful, and I'm inclined to say those are really similar predictions. So let's go ahead and do model dot comparison, and this is another flexplot function, and it just takes two arguments. So we'll go full underscore model and then reduced underscore model, and if we run that, we can minimize the plot now, and now why? Oh, okay. I know what happened. So I was wondering, normally there's a p-value and an r-squared over here, but it's not showing up. And I was trying to figure out why that was. And I know that p-values and r-squares only show up if you have nested models. If you need a refresher on what nested models means, go ahead and see the link in the description. But basically what that means is that the reduced model is nested in the full model if you can delete some terms from the full model to get the reduced model. But what happens here is we've got this interaction effect that is here, but it is not in here. So if we want to be able to have a p-value and an r-squared, we need to make those nested. So we could either do that by putting that term in there, which is exactly what I'm going to do, or we could delete this term. So now, boy, isn't it great when I make mistakes? I end up teaching you something you didn't know. Whoa, that went funky. Wow. So now it's generating vastly different predictions, but I'm inclined to say that maybe that's just capitalizing on the outliers. I don't know. So now that we have two models that are truly nested, now let's go ahead and do a model comparison. And so what do we get here? We got an r-squared of the full model of 0.2. So we're explaining 20% of the variance. And in the reduced model, we're explaining 17% of the variance. So by adding those interactions and the polynomials, we gain an additional 3% of the variance. I don't know, 3% is kind of a bit. And then we've got a p-value that is less than the traditional 0.05. Y'all know how I feel about p-values. I don't like them. But what this means is that if we use an arbitrary cutoff of 0.05, then yes, there is a detectable difference in fit between the full model and the reduced model. Interesting. So that, and when that happens, if there is a difference, then basically it's saying that one of these fits better, and we know that the full model is always going to fit better because it has more parameters. And so the p-value says we ought to go with the full model. What about the Bayes factor? So the Bayes factor of 7.8, that tells us that the evidence in favor of the full model is 7.8 times stronger than the evidence in favor of the reduced model. So that's not amazing as far as Bayes factors go. You know, the cutoff that people typically recommend is greater than 10. I like to see things in like the thousands. So according to the Bayes factor, it's a little on the ambiguous side. It's not necessarily better that the full model, or the full model is not necessarily better. But it is, at least in this data set, it is better. So if we look at the BIC has a smaller value, so that tells us we ought to favor the full model. And the AIC has a smaller value, so that tells you we ought to favor the full model. And by the way, this is a different conclusion than I reached before, because before when I was with the class, I didn't add that term in the reduced model. It was just a main effects model. And that changes the story, and that's actually very interesting. And a lot of people might be bothered by that fact that I ran it twice and got two different results, and I'm actually not bothered at all. I'm kind of comforted that in knowing that it's okay to be ambiguous. It's okay for things not to have a super right answer. So what is this telling us? This is telling us that it's probably important that we keep those polynomial terms and that interaction. I didn't realize that interaction would be so important, but it clearly is. And so I guess my take-home message, and we'll go ahead and look at the predicted difference. Basically, this is kind of sort of a visual representation of these lines. You remember how I was looking at those lines and I was trying to see if the difference between fit for those two lines is drastically different. And this tells you the quantiles of it. So this basically says, at minimum, there is no difference in fit between the two models. And we can see several areas, like right there and right there and right there, where they're generating identical predictions. The 25th percentile says they're differing by 0.2 points in the median, so on average or on median, the two models generate predictions that differ by half a point. Now that's actually not that big. But on the other hand, maximum, the maximum difference between those two, one model is predicting 11 points higher, or it could be lower, but I'm suspecting it's higher because I suspect it's over here. But this model predicts that probably that individual, or maybe that individual, it is predicting that their depression score is 11 points higher than that model is predicting. Well, hi again. So if I were to take all this evidence together, what would I conclude? I would not have solid conclusions at this point, nor should I, because I got two different answers when I ran it two different ways. So if we include that interaction term, it seems to suggest that, oh yeah, those polynomials are massively important. But if I don't do that in the model comparison, it says, well, it actually doesn't matter. And I can actually show you that. Let's go ahead and go back here. How's that sound? So if I were to, just to show you what I found with my students earlier, if we didn't have those terms that we were comparing, and if we were to visualize it, so they aren't all that different here. And then if we looked at the model comparison, yeah, in fact, I think this is even different. I don't even know. So now I'm curious about what I did before. I don't know. But this is saying that, okay, so this is saying that this model comparison, they're not all that different. So according to this model comparison, we don't need the polynomial terms. But again, with the other interaction, we did need the polynomial terms. So again, what are my conclusions? My conclusions are it's ambiguous, and at this point, we need more data. So this would be motivation to do a future study, or this sort of thing you could do on a holdout sample and then test it on the, or do a holdout sample, test it on the test set or the training data, and then test it on the validation data. And that's probably what I would recommend, is replicate it on another data set. Because at this point, it's ambiguous. It seems to be, if I were to make a conclusion, those polynomial terms are probably pretty important. But again, it's not 100% cut and dry. And that's how statistics should be. It's not how it often is. People often make super unjustifiable claims based on a very small data set. And even with this data set, it's a fairly large data set, I'm still gonna say this is kind of an ambiguous decision to make. And that's okay. We should be okay with that. So anyway, thanks for joining me, and I'll see you next time.